Hi everyone, welcome to my YouTube channel. In this video, I am going to discuss with you physical science KSET exam preparation, the concept of condensed matter physics. So, as we know, uh, the KEA is going to conduct the KSET exam. The syllabus has been already given. So, here are the core subject: mathematical method of physics, classical mechanics, electrodynamics, quantum mechanics, thermodynamics and statistical physics, and so on. So today I am going to explain you the topic from the condensed matter physics or solid state physics. And if you want to understand the complete syllabus or the paper, you will require a lot of time. So each and every concept takes its own time. So if you read thoroughly, you can easily crack the exam. So first you need to understand the given syllabus and read the each of the topic the core subjects from your MSc notes or the required notes for the preparation. Then you can able to solve the questions related to each of the core subjects. So here if you take the condensed matter physics or solid state physics, they have given the syllabus. So I am going to explain you about the basic ideas about crystal structure, Brevius lattice, Bragg's law, Miller indices, and many of the concepts. Today I am going to discuss. In one day we can't cover, or it is not like that the concepts. So you have to give proper time for each of the core subjects. Minimum 1 or 2 weeks if you give for the core subjects, you can thoroughly understand and prepare for the exam. So let us discuss the basic ideas about the crystal structure, and then we can go for solving the previous year questions. For the preparation of KSET exam, they are also helpful for NET or the GATE exam. And before going to start, if you are new to my channel, please subscribe my channel for upcoming videos on the exam preparation. So let us start. Crystal structure. So first we should know the crystalline materials are nothing but the example for solid. If you take any of the matter in nature, they exist in three forms. Either it may be solid, liquid, or gas phase. Okay. So solids, if we take, they have definite shape and structure. So solids are again classified into two types, crystalline and non-crystalline. So here we are dealing with the crystal materials. So first we should understand the difference between crystalline and non-crystalline. So crystalline are again classified into single crystal and polycrystalline. Non-crystalline are also known as amorphous. How we can distinguish them? Solid, as we know, the physical structure of solid and its properties are, if you take, they have proper shape and size, as we have classified into two types. So crystalline, if we take, the word itself indicates the orderly arrangement of atoms, ions or molecules, or we can say regular repeated arrangement of ions, atoms or molecules in three-dimensional pattern having definite geometrical shape. So single crystal, what does it mean? Single crystal are polyhedrons that have a distinctive shape for each material. For example, quartz, if you take, or the Rochelle salt are a good example for the single crystal. Atomic arrangement in single or monocrystal you can understand with the help of these images. A large single crystal of regular shape is called monocrystal. Other than these example, diamond and aluminum are the example for single crystal. Polycrystalline. The word poly means many. Polycrystalline solid consists of fine grains having a size of 10 to the power 3 to 10 to the power 4 angstrom, separated by well-defined boundaries and oriented in different directions. Within the crystal, the orientation or the direction of the atoms is different. You can understand with the help of these diagrams. Amorphous. If we take here this amorphous materials from externally they look or they have definite shape and structure, but internally the arrangement of atoms is not regular, or we can say irregular arrangement of atoms in case of amorphous solid. You can observe in this figure. So difference between amorphous and crystalline solid you can easily make it. First thing is atoms or molecules are periodic in nature in crystalline, and it is arrangement of atoms or molecules is not periodic. And here it is anisotropic in nature, crystalline, and amorphous is isotropic in nature, and they possess uniform chemical composition, and amorphous doesn't. Examples are sugar, sodium chloride, and quartz for crystalline material. Examples are glass, rubber, and sulfur. Space lattice. Space lattice is defined as the array of points arranged in a regular periodic fashion in 3-dimension space such that each point in the lattice has identical surrounding. Lattice is nothing but an imaginary concept. It is arrangement of points in space. You can understand with the help of this diagram. So basis. Basis is an atom or group of atoms that is associated with every lattice point, is identical in composition, arrangement, and orientation is called basis. Basis is nothing but the set of atoms or group of atoms which is attached to a lattice point. Here is the space lattice, and here is the symbol for basis which is attached to this lattice point. Basis is what? Group of atoms or molecules or ions. If these are attached to this lattice point, we can call it as a crystal structure. Space lattice plus basis. Unit cell. Unit cell is the smallest geometrical pattern whose repetition gives the entire crystal structure. Okay. Here is the unit cell, and some of the parameters you should know: alpha, beta, gamma, which we call them as interstitial angles. I am discussing with you here the very important points from this concept. So Bravais lattice. First, we should know what is lattice, and then Bravais, one of the French crystallographer, has explained that there are only 14 different ways of arranging identical points in 3-dimensional space with the help of 7 crystal systems. There are 14 Bravais lattices and 7 crystal systems. So crystal system, the set of values that the 6 lattice parameters, edges A, B, C, and the interstitial angles alpha, beta, gamma can be taken are limited to 7 only, and accordingly all the crystal structures have been classified. Cubic, first one, tetrahedral, orthorhombic, monoclinic, triclinic, hexagonal, and rhombohedral. These all are the 7 crystal systems. So you can distinguish them with the help of edges and angles. So unit cell characteristic you should know. Effective number of atoms per unit cell, atomic radius, nearest neighbor distance, coordination number, and then atomic packing factor. All these basic definition you should have. So atomic packing factor is number of atoms per unit cell to the volume of the unit cell. Void space, density. So once you have the definition of all these parameters, you can calculate these parameters for cubic lattice or cubic crystal system. Cubic crystal system has three previous lattices: simple cubic, BCC and FCC. So simple cubic crystal, if we take, it has 8 corners. Each corner is associated with one lattice point. That means 8 lattice points. Okay. BCC means body centered. It is having one atom at the middle of the unit cell. Face centered, there are 6 faces of the cube. So each face is having one atom at the center. So then you can calculate here the volume of the unit cell for simple cubic A cube. Atomic radius are equal to A by 2. Effective number of the number of atoms per unit cell 1 for simple cubic. Coordination number is 6 for simple cubic. Atomic packing factor is about 0.52. These all are very important in exam. Definitely they will ask packing factor, number of atoms per unit cell or the volume. Then void space is 48% for simple cubic. Density. Then BCC, if we take volume, is again same A cube, and atomic radius is given by root 3 by 4A. Number of atoms per unit cell 2. Coordination number 8. And packing factor 0.68. Void space 32%. So like that you can able to find out the parameters of each basic previous lattices. Similarly, the FCC structure, if you take volume, is again A cube, atomic radius A by 2 root 2. Number of atoms per unit cell 4 atoms. Coordination number 12. And packing factor 0.74. Miller indices. So Miller indices are specially used to designate the plane orientation and its direction. The method of designating a plane in the crystal by the set of 3 numbers H, K, L is known as Miller indices. There are 3 integers used to designate the plane in a crystal: direction as well as the orientation. Orientation is denoted in the parenthesis. If you use the square bracket, direction of the plane you can get. So steps to calculate Miller indices. Step 1. Identify the intercept of planes along 3 crystallographic axes, and if we take these 3 numbers which are inversely proportional to the intercept along 3 edges. Okay. So first step is to identify intercepts of the plane along 3 crystallographic axes. Then second step, determine the reciprocal of the integers. Then you should take the reciprocal of the integers, whatever the intercept you get. Reduce the reciprocal to smallest set of integer HKL by taking LCM. So you have to take the LCM of all those intercepts. Then you will get the integer which you can write in terms of parenthesis HKL by enclosing. This is the way to get Miller indices. First you should find out the intercepts and write them in the ratio or the proportion. Then take the LCM and you finally will get HKL values. So these parameters already I have discussed. Simple cubic 1 atom per unit cell, 2 atom per unit cell, BCC, FCC 4 atoms, radius, and coordination number of these 6, 8, 12, atomic packing factor, void space density. One more important topic, that is Bragg's law. And interplanar spacing is also very important. Compulsory one question will be there. The distance between the planes you can calculate with the help of interplanar spacing. It is given by the equation d square is equal to a square divided by h square plus k square plus l square. If it is a cube for cubic crystal, okay. If you are using other type of previous lattices, then you will get a square plus b square plus c square. So let us discuss about Bragg's law. Bragg and William Lawrence Bragg, both the son and father, a British physicist, derived this law in the year 1913. A simple equation relating the wavelength of X-ray to the angular position of the scattered beam and the separation of the atomic planes in crystal. So specially Bragg's law, also known as the X-ray diffraction law. When X-rays interact with the crystal structure, you will have the scattering angle. With the help of that, you can able to find out the construction of atoms or whole, the structure of the crystal material. So why X-rays have been used, not other radiations? Because X-rays are good enough to get the idea about the atomic dimension. The wavelength is going to match with the atomic dimension. That's why X-rays are used. So this is all about the basic idea about the today's topic I have given. So let us solve some of the questions here. So the first question, first question is about Miller indices. Find the Miller indices of a set of parallel planes which make intercept in the ratio 2a is to 3b on the x and y axis and are parallel to z axis. Any of the questions, if you solve, first try to understand the question because these questions are very sensitive. If you understand question, then only you can solve the questions. A, B, C being primitive vectors of the lattice. Also calculate the interplanar distance of the planes, taking the lattice to be a cube with the cube means all the edges are equal, and the interplanar spacing is that is 3 angstrom. They have given here each edge. So usually the distance here we measure in terms of angstrom. So let us solve this one. In this question, they have given the intercepts. If you have the intercepts, then only you can find out the Miller indices. So intercepts along x and y axis is 2a, 2b. On the z axis, they are parallel. That means if these two ratios are parallel, that means the intercept along z axis is infinite. That is understood. Planes in parallel to z axis. Reciprocal of the numbers. You should take the value of the numbers of these integers 2, 3, 2, 3 and infinity. So you should take the reciprocal 1 divided by 2, 1 divided by 3, 1 divided by infinity. 1 divided by infinity nothing but 0. So the smallest integer having the same ratio, you should take LCM. That means LCM if you take, you will get 3, 2, 0. So these are nothing but the Miller indices HKL. Then you can denote in terms of parenthesis. And this is the Miller indices you found from this given parameters. Again, you have to find out one more parameter here, interplanar spacing or distance. Here is the formula to calculate interplanar spacing, that is T equal to A divided by root H square K square plus L square. So A value they have given, that is 3 angstrom, and HKL values we found in the above solution. If you substitute, you will get the interplanar spacing or distance 3 by root 13. This is how you can calculate the interplanar spacing and as well as Miller indices once you understand the question clearly. Distance between the adjacent atomic planes in calcium carbonate is 0.3 nanometer. The smallest Bragg scattering for 0.3 nanometer X-ray is. That means you should calculate angle of scattering here. So they have given interatomic distance, that is interplanar spacing, that is 0.3 nanometer. Wavelength of the X-ray also they have given 0.3 nanometer. Bragg's law is given by n lambda is equal to 2d sin theta. So we have to find out theta here, scattering angle or diffraction angle. So sin theta is equal to, we can write it as n lambda by 2d. N is equal to 1 here, order 1. Smallest scattering is considered, hence we can take n equal to 1. Theta value, if you want to find out, first substitute wavelength and value of d, you will get 1 divided by 20. You can take inverse, sine inverse of 0.05 is equal to 2.9 degree. So this is the scattering angle. So option A is correct here. So the next question, for a sodium chloride crystal, the cell edge A equal to 0.563 nanometer. The smallest angle at which Bragg reflection can occur responds to a set of planes whose indices are. So the smallest angle or the scattering angle at which plane we can observe for the given edge of the cell. So here the cubic system relation between interatomic distance and cell edge is given by this formula. Miller indices HKL, Bragg's law, 2d sin theta n lambda. So sin theta is equal to 10 lambda by 2d. So theta for minimum, n must be 1. This is obviously obeyed. D must be maximum. So if we want to have angle minimum, then the value of interplanar spacing must be maximum, because they are inversely proportional from this equation. So for maximum D, that is A is equal to what, 0.5. The denominator is given by Miller indices. So it all depends upon the plane. So they have given 4 options here. Among these 4, which will give the maximum value of D, that is for the plane 1, 0, 0. If you take these planes, they will give high value of denominator, then value of D is going to reduce. If you want to get the high value of D, value of denominator must be minimum. That means it is corresponding to plane 100. So option A is correct here. Fourth one, silicon has diamond structure with unit cell A equal to 0.542 nanometer. Interatomic separation is. That means value of D we have to find out here. Interatomic separation. Unit cell edge is A, that is given 0.5. The interatomic separation, diamond has FCC. Yeah, obviously, it is a face center cubic crystal diamond. Then the radius, if you want to find out, it is given by for FCC structure standard equation. It is 4r equal to a root 2. Okay. You can also calculate here 2r by taking dividing by 2. Substitute value of a here and root 2 value. You will get the value of 2r. 2r is nothing but the interplanar spacing. The interatomic distance is equal to twice of the radius, diameter we can say, 0.383 nanometer. Option C is correct. If the ionic radii of Mn and S are manganese and sulfur are 0.8 and 0.184 nanometer respectively, the structure of MnS will be. They have given the ionic radius of Mn and S, two atoms. If we have the molecule that is manganese sulfide, that is equal to the structure. They have given 4 options: cubic close packed, body centered, NaCl type, primitive cubic cell. So if it is ionic best example is sodium chloride. Manganese is positive, sulfur is negative, like sodium chloride, sodium positive, chlorine negative. So it is ionic crystal. So ionic solid MnS will have NaCl type crystal structure, that is FCC crystal structure. So the next one, in crystallographic notation, the vector OP in the cubic cell in the figure is. So vector OP is given by the values here, integers. You can first note down them. Vector OP is equal to, along 3 axes, a comma a by 2. You can take the numbers only in the bracket 1 comma 1 1, that is given by the direction of the plane, 1 1 1 by 2. If you take the coefficient of these value of edges, 1 1 1 by 2. If you take the LCM, you can write here the vector OP notation, crystallographic notations, plane, direction. If you write this in terms of square bracket, that gives the direction of the plane. If you write in terms of parenthesis, that is the orientation of the plane. So here, if you take the LCM, you will get 2 2 1. This is the crystallographic notation for vector OP in the given cubic cell. Next one, the powder diffraction pattern of a body centered cubic crystal is recorded by using copper K alpha X-ray of wavelength 1.54 angstrom. Then in this question, if the plane 002 plane diffract at 60 degree, the lattice parameter is. And the second question, assuming the atomic mass of the constituent atom to be 50.94 atomic mass unit, the density of the crystal we have to find out. First thing, the powder diffraction pattern. There are different ways to study the diffraction pattern of crystal. Using Bragg's law or powder diffraction method also has been used. There are two questions here. In the first question, they have given the plane value for the copper K alpha 002, angle T, scattering angle 60 degree. Wavelength also they have given of the X-rays. So equation to calculate D, substitute values, I will get value of D, that is A by 2. Bragg's law, 2D sin theta equal to n lambda. Substitute values here. Here you should find out the lattice parameter, that is A. That is smallest diffraction, that corresponds to n equal to 1. Then if you substitute in this formula, you will get 1.78 angstrom, which is the value of lattice parameter, but in the given option it is not there. Then by taking second order, let us calculate. It is near to the value 3.56 angstrom. So that means option C is correct. That is for the second order diffraction pattern. In the second question, assuming the atomic mass of the constituent atoms to be, density we have to find out. Mass they have given, atomic mass. Density is given by Nm divided by Na cube. M is the mass of the copper. K alpha 2 into 50.94. N, Avogadro number. A is the atomic lattice parameter. Then the density is given by 3.75 into 10 to the power 3 kg per meter cube. Density of the crystal, 3 point, option A is correct. So like that you should solve the given problem. Here first thing is to remember the formulas related to all these concepts. Then only you can solve. Next one, consider the atomic packing factor of the following crystal. Simple, BCC, FCC, diamond, and T is for hexagonal close packed. Which two of the above structure have atomic packing factor? So they have given each of the lattice with their symbol P, Q, R, S, T here in this order. P stands for simple cubic. Atomic packing factor 52% we know. PCC 68. FCC also, FCC 74%. Diamond 34 they have given. Hexagonal closed pack 74. From above table it is clear that AP, atomic packing factor of FCC cubic R and hexagonal closed